Good morning, everyone. Before we start, I'd like to mention something I noticed recently. I've heard several people say that optimization is the same as AI, or that optimization itself is AI. That made me realize there can be some confusion between these two concepts. So, I decided to prepare this short presentation to clarify the differences between artificial intelligence and optimization, explain where they overlap, and show how they actually complement each other in real-world engineering applications. By the end of this presentation, I hope the distinction will be much clearer. Although AI and optimization are related, their goals are different. AI focuses on intelligent behavior. It aims to recognize patterns, support decision-making, adapt to new situations, and handle uncertainty. Optimization has a much more specific objective. It tries to maximize or minimize an objective function, such as reducing cost, minimizing energy consumption, maximizing efficiency, or improving performance while satisfying constraints. Their approaches are also quite different. AI is mainly data-driven. It learns from historical data using machine learning, deep learning, or reinforcement learning. The system improves as more data becomes available. Optimization is model-driven. Before solving the problem, we first define mathematical equations, objective functions, and constraints. Then, optimization algorithms search for the best solution. Here are some practical examples. AI is commonly used in image recognition, natural language processing, speech recognition, recommendation systems, and autonomous driving. Optimization is widely used for scheduling, route planning, power flow optimization, engineering design, resource allocation, and production planning. These examples show that AI is often used for intelligent prediction, while optimization is used for selecting the best decision. The outputs produced by these methods are also different. AI models are generally predictive and probabilistic. Since they learn from data, their predictions may vary depending on the training data, and they don't always guarantee the mathematically optimal solution. Optimization methods are usually deterministic. If the mathematical formulation stays the same, they consistently produce the same optimal solution, especially for convex optimization problems. And this is important to know. AI depends heavily on data. Without sufficient and high-quality data, AI models cannot learn effectively. Optimization depends less on data and more on having a well-defined mathematical model, including an objective function and constraints. So, AI needs data while optimization needs a mathematical formulation. One major difference is learning. AI systems learn from experience. Machine learning, deep learning, and reinforcement learning continuously improve their performance using data. Traditional optimization algorithms do not learn. They simply solve the mathematical problem that has been defined. In other words, AI becomes smarter through learning, while optimization computes the best solution directly. Even though they are different, AI and optimization work very well together. Scenario A. Optimization in AI optimization is the engine that allows AI models to learn from data. When training a neural network, algorithms like gradient descent are used to minimize prediction errors. By tuning internal settings, optimization helps AI turn raw data into accurate insights. Scenario B. AI in optimization requires clear mathematical equations, but real-world problems can be too complex to model cleanly. In these chaotic situations, AI steps in as a surrogate model or smart heuristic. AI predicts shortcuts, allowing optimization tools to solve highly complex problems. So AI and optimization complement each other rather than compete. In summary, AI provides data-driven learning and adaptive intelligence. Optimization provides structural precision and direct mathematical efficiency. Both approaches have advantages and limitations. AI is excellent at recognizing complex patterns and handling unstructured data like images, audio, and text. However, it usually requires a large amount of labeled data and cannot guarantee an optimal solution. Optimization provides mathematically interpretable solutions and can guarantee the best result for well-defined problems, especially convex ones. However, it becomes difficult when the problem cannot be accurately modeled mathematically. Here are some commonly used algorithms. In AI, popular algorithms include convolutional neural networks, recurrent neural networks, transformers, reinforcement learning, and decision trees. In optimization, common methods include gradient descent, linear programming, nonlinear programming, mixed integer linear programming, genetic algorithms, particle swarm optimization, and other evolutionary algorithms. Interestingly, gradient descent belongs to optimization but is heavily used inside AI for training neural networks. Let's look at engineering applications. AI is commonly applied to predictive maintenance, fault diagnosis, quality inspection, computer vision, and load forecasting. Optimization is used for unit commitment, economic dispatch, scheduling, engineering design optimization, and resource allocation. In many industrial systems, AI predicts what will happen, and optimization determines the best action to take. To conclude, AI and optimization have different purposes but are highly complementary. AI focuses on intelligence, learning, and decision-making from data. Optimization focuses on finding the best solution to a mathematical problem. In modern engineering applications, combining AI with optimization often provides the most powerful solution. AI supplies intelligent models and predictions, while optimization ensures efficient and optimal decision-making. If you need more information, we will be happy to talk to you.